Hi everyone, welcome to lecture 28 on hypotheses and deduction. The objectives for this video are the following. After watching, everyone should be able to, number one, show how a hypothesis gets refuted, and number two, show how a hypothesis gets corroborated. So this is the penultimate lecture of the class, and I said last time that we'd return to some of the ideas that have come up in the course so far and use our work on probability theory to shed some light on those issues. Now, the first of these ideas is hypotheses and evidence. Really, of course, this came up in our journey through Bayes' theorem itself when we talked about the odds form of Bayes' theorem, but we can link the ideas to our discussion of scientific inductive logic as a whole as well. Now, we've said before that science aims to put forward hypotheses that predict phenomena. We then go out into the world and look or do an experiment. If we don't see that phenomena, the hypothesis is said to be refuted or falsified. And if we do see that phenomena, the hypothesis gains some sort of plausibility. The question is, why do we falsify hypotheses or think that they gain some sort of plausibility on the basis of our observations? So let's talk about falsifying hypotheses first. Suppose we have a hypothesis H and we deduce an observational prediction from it. Let's call it E. Then if we test the prediction and observe that it's false, the hypothesis cannot be true, so the hypothesis gets refuted. A deductively valid argument, remember, cannot lead from a true premise, the hypothesis in this case, to a false conclusion, which is the prediction in this case. Now this is straightforward when the reasoning is deductive, but what about inductive reasoning, which after all has formed the bulk of the course? That is, what about hypotheses that don't tell us which occurrences are impossible, but only which are more or less probable? Unfortunately, Bayes' theorem can explain hypothesis falsification or corroboration, even in the case of probabilistic reasoning. We will spell out each case, falsification and corroboration, to see how. Now, I know people were asking for more concrete examples a few weeks back on the 5-minute paper, so we'll walk through two examples that hopefully correspond to people's idea of more concrete. We're looking at falsification first, remember. So, suppose it's 1801 and we're interested in the problem of determining whether light is a wave or a particle. We've done a bunch of research on things that behave like particles and things that behave like waves, and we can predict the behavior of each reasonably well. We don't know whether light is a wave or a particle though. So we set up an experiment as follows. We shine a light source, let's imagine it's a laser, at a plate, and in the plate are two small parallel slits. We observe the light passing through the slits on a screen behind the plate, and we don't know beforehand what to expect. So first, let's suppose we're someone who puts forward the following hypothesis. Light behaves only like a particle. So this is our hypothesis, let's label it P for particle, and we have a certain degree of belief in it, P of P. Now, what would we expect to see on the screen once we shine our laser at the plate if light behaves as a particle? Well, from our research on particle behavior, we might expect to see two small dots of light on the screen. A bunch of electrons pass through one slit, and they all continue on in a straight line and hit the screen behind the first slit, and similarly, a bunch of electrons pass through the second slit, they all continue in a line, and they hit the screen behind the second slit. That's how particles behave. So what we end up with would be two concentrated spots of light. Then this, two concentrated spots of light on the screen, is a prediction, let's call it C, made on the basis of our hypothesis P, that light behaves like a particle. So let's pause here for a question. Well, our degree of belief in the prediction C given the hypothesis P should be 1, because the hypothesis implies that prediction. That is, we deduce the prediction from the hypothesis. And similarly, we can ask, what should our degree of belief be in not C given the hypothesis P? Well, it should be 0. We cannot think C will not occur given the hypothesis P if we think that C follows from P. So we carry out the experiment, and on the screen we see the following pattern. Not two concentrated spots of light, but bright and dark bands on the screen called an interference pattern. So we have not observed what we predicted. And so what are we to make of our hypothesis? Well, we started out with some degree of belief in the hypothesis that light behaves only as a particle. Then our new degree of belief in the hypothesis on the basis of our observation is P of P given not C, because we observed not C. But Bayes' theorem tells us that P of P given not C equals P of not C given P times P of P, all divided by P of not C. And we said before that P of not C given P is 0, because we deduced C from P. So the right-hand side of that expression there is 0. Then the left-hand side, P of P given not C, is also 0. Or our degree of belief in our hypothesis on the basis of what we observed is 0. And in this way, the hypothesis P that light behaves only like a particle is refuted or falsified on the basis of our evidence, what we observed on the screen. So this is how Bayes' theorem tells us how hypotheses are falsified on the basis of a certain observation. So what about corroborating hypotheses? So let's suppose it's still 1801 and we're about to perform the same experiment again. Suppose this time though we put forward an unusual looking hypothesis. Suppose we think light behaves both as a particle and as a wave. Let's call this hypothesis B for both. Then what would we expect on the basis of this prediction? Well, let's say we've done our research again and we make the following clever deduction. We predict that because of the wave nature of light, the light waves passing through the two slits will interfere, producing bright and dark bands on the screen. However, because of the particle nature of light, we predict that the light will always be found to be absorbed at the screen at discrete points as individual particles. So let's call this prediction D for dual nature. And let's pause for a question again. Because this is a deduction from our hypothesis, we have P of D given B equals 1, and we have P of not D given B equals 0, similar to what we said before. Now suppose we perform the experiment and we see the interference pattern from before of bands of light, and on closer inspection we find out that indeed the light is absorbed on the screen at discrete points. In other words, our prediction was correct. So what do we make of our hypothesis on the basis of observing a correct prediction? The new degree of belief in our hypothesis is now equal to P of B given D. Let's also say that the hypothesis is corroborated by the evidence if P of B given D is greater than P of B, i.e. if the evidence D increases our credence in B. That is to say, the hypothesis B is corroborated by D if P of B given D over P of B is greater than 1. But what do we know from probability theory? Well, probability theory tells us that P of B given D over P of B equals P of D given B over P of D. And since we deduced D from B, P of D given B is 1. So P of B given D over P of B equals 1 over P of D. And since we were assuming that we were uncertain to some degree about whether D would obtain or not, then P of D is strictly less than 1 and it's strictly bigger than 0. So the right hand side is greater than 1, and so the left hand side, P of B given D over P of B, is also greater than 1. That is, the evidence D corroborates our hypothesis B. So this is how our work on probability theory can help us make sense of how certain observations increase our confidence in hypotheses, how those predictions corroborate those hypotheses. We'll leave that discussion here. You can expect to see more scenarios like this one. So as long as you can translate these examples into the language of Bayes' theorem, identify your hypotheses, your evidence, or the observation of your predictions, and show how a hypothesis is either falsified or corroborated on the basis of those observations, then you'll be good to go. Next time, we'll talk about evidence some more, and we'll round off the class by discussing convergence to the truth. So have a go at your self-reflection questions, and I'll see you all next time.